Hey y'all, welcome back to Sidewynders Shed. Now I'm sitting here at work, waiting on a load, don't have a whole lot to do, so this is where my mind goes. Again, I'm thinking of, time dilation, and more importantly, how speed affects time, using Einstein's theory of special relativity. What that states is the faster you move through space, the slower you move through time, i.e., time slows down. His theory of general relativity also says that time can slow down due to gravity. The closer you get to a singularity, the slower time will move. So if you get close to a black hole, the closer you are and the stronger the gravity is, the slower time will move for you. So if you get caught close to the gravity well of a black hole for 10 years, 3 years, 7 years, something like that might pass for you, but for people on Earth observing you, you were there for 10 years. Same with his theory of special relativity. The faster you go, from your perspective, you being the traveler, the slower time will move for you. You don't notice a difference. From your perspective, time is moving the same as it always has. But from an outside observer, from somebody on Earth, you would be moving slower. So therefore your time would be moving slower, all the way down to a cellular level. Alright, for example, our nearest star is Proxima Centauri. It's roughly 4.24 light years away. If we were able to build a spaceship and launch you into space at 99% of the speed of light, I mean immediately, no build up, no slow down, but just immediately launch you at 99% the speed of light, and you got to Proxima Centauri without crashing into it and just stopped from 99% the speed of light to zero, say it's feasible, that just gets rid of all the other variables. It would take you from Earth time, somebody watching you on Earth, it would take you 4.28 years to go the 4.24 light years. Okay, everyone with me? It makes sense. You're not doing 100% the speed of light, so it's going to take you a little longer to get there. Okay, however, you as a traveler, you as a passenger on this spaceship, it would only seem as though basically 6 months and 3.5 weeks had passed. A half a year, roughly. 7 months. We'll round it to 7 months. You would be traveling in that spaceship yourself for only 7 months. That's how slow the time, or what the time differential, time dilation would be between you as a traveler and somebody from Earth. Like I said, on Earth time, it would still take you 4.28 years to get there, but you as a traveler would only experience traveling for roughly 7 months, not 4.28 years. So what this brings into question is, we live in a very dynamic universe. Everything is moving, nothing is stationary. The Earth spins on its axis at about 1,000 miles an hour at the equator. 24 hours makes one day. That's the Earth is spinning 1,000 miles an hour in order to make a complete circle on its axis in one day, in a 24-hour period. The Earth also orbits the sun, goes around the sun in 1 year, 12 months, roughly, at roughly 67,000 miles an hour. That's how fast it is traveling around the sun. So it's spinning at 1,000 miles an hour, and it's orbiting the sun at 67,000 miles an hour. Not only that, our sun is not stationary. Our sun is also moving through space in one of the arms of the Milky Way galaxy, and it's going around the center of the Milky Way galaxy at roughly 448,000 miles an hour. Let's just take that measurement. So even though we feel like we're sitting still, not going to factor in the fact that the Earth is spinning or that it's orbiting the sun. We're just following the sun, and we're moving along with the sun. The whole solar system is moving along with the sun through space at 448,000 miles an hour. We'll call that, from our perspective, because we don't feel it in real life, we'll call that zero. Okay, we're here. Now, let's say at the very edge of the Milky Way galaxy, there's another solar system that's keeping up with us. Okay, if we're moving at 448,000 miles an hour, that other solar system at the edge of the Milky Way galaxy has got to be moving, we'll say, twice as fast as us to keep up with us. So we go around the center of the Milky Way at the same time. Think of it this way: it doesn't matter, any oval track, any circular track, any oval track, the inside lane versus the outside lane, in order to keep up with somebody, whether they're on foot, in a car, on a bicycle, whatever, they don't have to go as fast as you do in order to stay up, stay even. You have to go faster. If you're twice as far apart, I don't know if it actually works this way. I haven't done the math or looked into it, but let's just say, for argument's sake, to keep everything simple, if you're twice as far away from them, from the center of the track, you have to go twice as fast as they do just to stay even with them. Now, I know it's a multiple of pi and stuff like that, so 3.14. I don't want to get into that right now. But anyway, my biggest thing is, due to time dilation and the faster that you move through space, if we're moving at 448, we'll call it 450,000 miles per hour around the Milky Way, and we find a star that's moving at 900,000 miles per hour, so they're keeping even with us. They're just further away. They're on the outside lane. We're on the inside lane. Does that mean time for any living entity on that planet moves slower for them than time does for us? I.e., we look at them and we go, we've been watching, let's say we could see their civilization, and we can say, all right, yeah, we just saw this year, their signs of their first radio emissions. Well, for the next 500 years, we see not a whole lot of progress. And that's because, from our perspective, or from their perspective, time was moving slower, so only 200 years have passed for them, not 500. That's my question. Because we're moving at different speeds through space, does the time dilation affect that other planet? These are just stupid things when I'm sitting here bored that I can think of. Does it have any bearing or effect on my life? No. Is there something else I could be thinking about? Oh yeah, definitely. Most important, how to keep the missus happy so I stay out of the doghouse. That's a very important thing to think about all the time. But for the moment, I did really good over the weekend. I got enough brownie points. I should be able to sit here and mull this over for an hour or two. Other than that, after that, yes, I'm going to go back to figuring out how to keep the missus happy. So, happy wife, happy life. You know how that goes. But anyway, yeah, just if anybody has any thoughts, ideas, or knows more than I do, you know, it's hard to wrap your head around the fact that time is not a constant. Time is relative. Time is variable, depending on your speed or gravity. All joking aside, I won't get into a few jokes about weight or laziness or anything you can throw in there, but on a real scientific scale, I mean, experiments have been done with nuclear clocks, one sitting still, relatively still, you know, it's not moving on Earth, and another one put on a high-speed jet. The one that was on the high-speed jet, when they brought it back and they compared the times between the two, the one that was on the jet was running behind the one that was stationary. This is a proven fact. All our satellites, space probes, especially GPS satellites, they all take this time dilation into consideration so that they fire their rockets, they stay in a geosynchronous orbit if they need to. They know where they are at all times. So it is something that's been proven. Matter of fact, NASA did an experiment with a set of twin astronauts, one that had stayed on the space station for a lengthy amount of time and one that has not been into space and did not spend any time on the space station. The one on Earth is a few microseconds older than the one that spent time on the space station. Actually, I think it might have come up to almost a minute or so. It was something measurable. You can check it. I don't have the exact details. But, so it is something that is true, and it's a fact. The faster you go, the slower time moves. If somebody was in a spaceship moving at 99% the speed of light, and we were able to have a real-time audio-visual account of what was going on, two-way, let's say we used a quantum entanglement video processor, video-audio communication system, where we can see what's happening in real time. Looking from our perspective on Earth, looking at the people in that spaceship, they would be moving at roughly 1/4 the speed of what we are. Vice versa, if they're watching a video of us sitting at mission control, it would be like them watching a video of us at 4 times the speed. This is all rough estimates here. It's close, but it's rough estimates. Heck, it might even be 8 times the speed. Yeah, I think it'd be closer to 8 times the speed. There'd be 8 times the speed different. They'd be moving 8 times slower. We'd be moving 8 times faster, depending on perspective relative to each other. So like I said, if that happens just locally, what about further away when you have a planet that is traveling through space at twice the speed we are? Although it's not anywhere near the speed of light, would there still be those microseconds, milliseconds, maybe even seconds or minutes of time dilation? Would a year on Earth be half a year, 3/4 of a year, a quarter of a year passing? You know, if we were able to synchronize 2 clocks from each planet to Eastern Standard Time, at the end of the day, would they show the same time? Or would the one that's moving twice as fast, just like the one that was in the jet aircraft, be behind the one that was on Earth? just a thought. If anybody has any more information, smarter than me, which most of you are, or can, hook me up with Neil Tyson deGrasse or something like that, go ahead. Leave a comment, a link, whatever. Give Neil a link to this video for me. But leave some comments. And hey, thanks for listening to me babble again. And thank you all for subscribing. Like I said, I'm just kind of bored at work and already got enough brownie points with the wife right now to keep me out of trouble for a couple hours. So y'all take care. Have a good day.